Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa ElDiwiny, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks. Hello and welcome to IEEE Soft Robotics podcast. Could you please introduce yourself?
Yes, my name is Josh Bongard. I'm the Cyril Weinot Professor of Computer Science here at the University of Vermont in the United States.
Mm-hmm. So I would like to ask you first, when you first build a robot and what's your feeling at this time?
When did I first build a robot?
Yeah.
I first built a robot when I was 13, and I got a robot as a Christmas gift. And I was very excited to receive this robot, and I built the robot, and the robot could barely do anything. And first, I was very surprised, and then I was frustrated because I had also received that year my first personal computer, and this was back in the 1980s. And even back then, the very simple Commodore 64 could do pretty much anything if you could figure out how to program it. So from an early age, I was surprised by how easy it was to get a computer to do something and how difficult it was to get a robot to do something, which more or less is still true today. And trying to overcome the obstacles posed by robotics remains my life's work.
Nice. So you really have been known as evolutionary robotics, but I would like to know how you came to robotics. Of course, there's many interesting thoughts you have proposed many times, that how you came to soft robotics, how you decided to be in soft robotics.
In soft robotics?
Yeah.
So I did my PhD with Rolf Pfeiffer at the University of Zurich back in the early 2000s. And at that time, Professor Pfeiffer was extremely interested in embodied cognition, and he and I went on to write a book on the subject. And he was really focused on not just this issue of morphology or the body plan of robots, but also their material properties. So for Rolf, this was something that was perhaps as important, if not more important, than three-dimensional shape. But back in the early 2000s, it was extremely difficult to build a robot made out of different material properties. So there were a lot of interesting ideas going on in the Pfeiffer lab at that time about what we could achieve if we could make robots out of soft and hard materials, if you could create a robot that had a gradient of different kinds of materials throughout its body. But most of that work was sort of thought experiments and theoretical work at the time. Now, 10, 15 years later, we obviously are able to build robots out of very exotic materials. So it's an exciting time to be working in soft robotics because we can now try and instantiate or actually test some of those theories about why soft robots might be advantageous to rigid robots under certain circumstances.
Great. So before going to your work in soft robotics, I would like to ask you how you would define soft robotics from your perspective and experience. Because there's different definitions here.
Absolutely. I think I'm in agreement with a lot of my colleagues who work in this area that soft robotics is maybe an unfortunate name for this branch of robotics because soft robots is to traditional robotics as nonlinear dynamics is to linear dynamics. The former field is somewhat a generalization and contains the latter field. So linear dynamics are sort of a specific case of nonlinear dynamics where the nonlinearities are identity. They don't exist. In the same way, a traditional robot that's maybe made out of rigid parts, there may be a few small soft parts in there, but a soft robot is interesting because it's usually not just completely soft, but some interesting amalgamation of soft and rigid components. So for me, soft robots are not just robots that are 100% soft. Instead, this term soft robotics forces us to think not just about the control policy of the robot, but also about the body itself. What is its shape? How might it exploit its softness to change shape? And what is the material properties of the robot itself?
Yeah.
So that would be my definition.
Great. So now we would like to know what's actually recent workings of robotics to our audience.
Sure. We've got several projects ongoing in the lab. One of the ones I think that's most relevant to your audience is recent work that we reported this past summer at the RSS conference, the Robotics, Science and Systems conference. That was work by my PhD student, Sam Kriegman, and also a collaboration with our colleague, Rebecca Kramer-Botiglio at Yale. And in that paper, what we demonstrated is that you could have a soft robot that experiences deep insult. So by deep insult, we mean not just some slight form of damage, but for example, losing half of its body mass. Perhaps the robot is cut in half. And what we demonstrated in that paper is that soft robots are uniquely suited to dealing with that kind of deep insult. What we found is if we allowed these deeply damaged robots to try and recover, they weren't able to recover so much by adapting their control policy, but keeping their damaged shape constant. Instead, evolution was better able to find a compensating shape for the robot. In some cases, the damaged robot would grow back the lost limbs, and it could carry on moving with its pre-damaged control policy. Even more interesting than regenerating lost appendages, some of the robots would actually evolve completely new shapes that allowed them to keep moving with their pre-damaged control policy. So that was kind of interesting to us because, again, it suggests yet another advantage of soft robots over traditional robotics, which is using shape change as a novel way of recovering from damage.
That's a very fascinating point, and I think many questions here coming about what kind be that application behind this approach. And before going to more questions about, do you think that because you highlighted in your box about that the shape is important, and I would like to ask you what do you think about embedded intelligence or just morphological computation? Which direction do you think is worthwhile to go in soft robotics research? Because I think this is really very interesting point.
Right. So as I mentioned, sort of my definition of soft robotics is not the target itself, the soft robot, but rather, working with interesting materials forces the roboticist to really think about embodiment, the shape of the robot, the material properties. And by thinking differently about robotics, it takes you in new directions. So as in the experiment that I just described to you, it's actually not the shape itself that's important. It's the fact that a soft robot can change shape. This is something that is difficult or impossible for a rigid robot to do. In that most recent experiment, we showed that shape change allows the robot to deal with unexpected internal change, which is severe damage. We have some other ongoing work that shows shape change is equally useful for dealing with unexpected external change, like, for example, coming upon a new environment, moving from flat ground onto a slope or rough terrain. Perhaps the current shape that the robot uses to move over flat terrain, that shape is no longer appropriate for moving over rough terrain. So depending on your definition of morphological computation, it's at least an additional kind of morphological intelligence where the machine is now challenged not just to think about how to adapt its control policy when it experiences internal or external change. It has a new option open to it, which is to also change shape or maybe even change material properties. There are new exotic materials that are coming online that may allow soft robots of the future to dynamically stiffen and soften their bodies. This is a concept known as programmable stiffness.
So given a situation that is change or the damage is happening to soft robotics that you develop, how they can develop a new strategy of locomotion? It is just something coming by autonomously, is this kind of motion happening? I don't know if you really tested in a real robot yet, But this is really interesting how they can develop a new locomotion based on the damage happening to the soft robot.
Exactly, yeah. So in this RSS paper from last summer, we demonstrated a hardware prototype, and we're continuing to work on that hardware prototype with our colleagues at Yale that does indeed allow a physical soft robot to change shape. And given its new shape and its environment or its damaged state, there are new sets of control policies and new behaviors that are available to the robot in that shape or that circumstance. And that's kind of a new way of thinking about, training robots, and opens up lots of interesting questions from an optimization and design point of view. For example, how do you go about designing a robot that can easily change shape or change into as many possible shapes as possible, or find a shape which then quickly allows it to find a new control policy? Those are all potentialities of this robot, and you can imagine those in turn becoming objective functions against which you design a robot.
So I would like to ask you about intelligence of robotics. How you would see the intelligence in soft robotics, in terms of the body, or just we have to invest more in coming up with brains for soft robotics. How you would see it in general, intelligence in soft robotics?
Sure. So as my advisor said, and many have said before us, intelligence is a notoriously difficult term to define. But for most people, they have an intuition about what it means. And a lot of people would probably agree with the statement that intelligence is somehow about being able not to become trapped in the future, or to keep your options open in the future. That's an important hallmark of intelligence, and different organisms realize that in different ways. And one of the ways that humans make sure that they can keep their options open in the future and invade other ecological niches is not necessarily changing their body. That's not something that's very easy for humans to do, but we do wear scuba gear when we go underwater. We've designed spacesuits for exploring outer space. We get inside a car. We wear gloves and operate tools. All of those you can think of as what Andy Clark, the philosopher, called the extended phenotype. They change the sensor motor possibilities of the human wearer. And so I think that same intuition applies to soft robots. A robot that can change its shape has a broader range of sensor motor dynamics that are available to it than a rigid robot that cannot change shape. And if you have more sensor motor possibilities available to you, if you have a search method running or a learning algorithm running to exploit that broader range of possibilities, you have a better chance of avoiding damage or death or injury in future. You can avoid getting trapped in future situations. So I think in that sense, you can imagine a very clear connection between shape change and intelligence.
So I would like to ask you about what is the most misconception about soft robotics? Something is misunderstood maybe in the research about soft robotics. If there is any points you think is about misconceptions?
Yeah, I think there are some misconceptions about any new academic discipline, and soft robotics is no exception. One of the ones that I've noticed is sort of this misconception that soft robotics is just kind of about eye candy, making cool videos where you have a robot that's made out of some exotic material and it can twist and contort itself in some interesting way. Which is all true, but it's not just a stunt. That there is something very, very fundamental about soft robotics that suggests such robots would be of increasing utility in the future. We may be able to make soft robotics more intelligent than rigid robots for the reasons I just described. So, I think it's important in this new field of soft robotics that this notion of play, that we just try out different materials, try and put new technologies together in new ways to just see what's possible. but to realize that that's not all that the field is about. The field is about using those new materials to force us to think differently, and importantly, to think more broadly about the nature of embodied intelligence.
Oh, that's great. So I would like to ask you about what could be the questions that haven't been asked yet in research. Do you think there's any questions that we didn't take in consideration yet in the research of robotics in general?
Well, I think, they're related to soft robotics is the field of biohybrid robots. So these are machines that are made up partly of artificial materials, but also biological materials. Obviously, in nature, every single species is not completely rigid. All organisms, for good reasons, are mixtures of hard and soft parts. And if we're going to make soft robotics, or we're going to make machines that are combinations of soft and rigid materials, it makes it even easier to integrate them with biological materials. And I think this is a huge untapped potential in both fields, which is how do we bring together the best of both worlds? How do we combine artificial materials, many of which are stronger and more durable than biological materials? But how to also exploit biological materials, which are much better than our materials at regrowing and dealing with damage, altering their form and function as the environment around them changes. I think soft robotics and biohybrid robotics offers a great opportunity to bring together the best of human-made and biological materials.
That's a good point. I would like to ask you about what do you think about smart material like electroactive polymers? Do you think using a smart material could be promising? Because we all are aware there is still limitation in terms of performance. So I don't know what you think, because some materials may be passive and we use techniques, as you highlighted, morphological computation, or maybe we go to smart material. So which one do you think about it?
Yeah, I think smart materials is all part of the same package here, which is, if we're thinking about useful machines, performance is not the only feature we would like to see in these useful machines. Obviously, it's important, but it's not the only one. We've gotten pretty good in robotics about making specialists. We can make a robot that does one thing and does one thing well, and in a lot of cases it does it better than a human does. But we're not very good at making machines that are generalists, that can adapt what they do given changed circumstances or a different command from its human operator. But smart materials, like you mentioned, programmable stiffness, biological materials, they're all very good at reconfiguring into new forms and therefore providing new function as the world around them changes. So I think the biggest potential for soft robotics is to be performant, maybe not optimal, but to do well for a given circumstance, but also to be very pliable, that the machine itself can mold itself into new forms and functions to perform new tasks. This has been an open problem in robotics about how to create generalized machines since the very beginning. And I think soft robotics gives us a unique opportunity to address that challenge.
So I would like to ask you about simulation of soft robotics, because do you think that we reach this point that we have sim to real, we have the same performance in reality given in simulation?
Yeah, so sim to real, that's an interesting topic. I've worked on this for a number of years now. Sim to real is always challenging. And there is an intuition, and I would say perhaps even a misconception, that sim to real is even more challenging for soft robots than it is for rigid robots. But we have some work going on in the lab that shows that is not necessarily the case. If you can exploit the properties of soft materials in the right way, you can actually narrow the sim to real gap. We don't have any work published on this yet, so I probably won't say too much more about it. But again, soft robots causes us to think differently. In this case, to think differently about the sim to real gap.
So what are the challenges you're already facing now and in your research challenges you have?
Some of the challenges. So some of the challenges have to do with actually constructing these robots. So in my group, we focus mostly on evolutionary optimization and simulation technologies. And we collaborate with our colleagues at Yale and elsewhere where they have expertise in building physical soft robots. But of course, manufacturing soft robots is particularly challenging because now there are also material science questions that need to be tackled. So this makes things particularly challenging. How do we go about evolving interesting robots in simulation that are made up of complex combinations of exotic materials, but ensure that those complex arrangements of exotic materials can actually be realized in manufacture. So the sim to real challenge is actually not so much in transferring the behavior, but actually transferring the design itself. Can you actually manufacture the designs that evolution discovers in simulation? That's a big open problem, I think, in this field.
So I don't know what you think about this speaking different language, because I think you have been lucky to know many backgrounds. But do you think in soft robotics now there's a challenge of speaking different language? Do you see any challenges in this regard?
What do you mean by speaking different languages?
From mechanical engineering to material science, electrical.
Yeah, absolutely. And I think, again, this is one of the challenges of doing interdisciplinary work. But again, this is a challenge and an opportunity. We spend a lot of time in my lab talking not just about how to collaborate, about how to transfer a given design to our mechanical engineering colleagues, but also how we can learn to, as you say, how we can learn to speak the same language. I put a lot of emphasis in my group about having my students go and spend time in the labs of mechanical engineers and vice versa, and really emphasize this technology transfer and expertise transfer by having students and postdocs move from lab to lab. I think this is the way that science is going to play out in the 21st century, is that the really interesting questions lie at the intersection of very different fields. We have to think differently about how we educate our students to be able to speak the same language, to be able to communicate with their peers from very different fields.
So I'm interested to know about what application you'll be interested in applying what you developed already when you have soft robotics that can adapt shape given the damage.
I think a lot of the clinical applications are particularly interesting. We're getting better at creating. Our lab and other labs are getting much better at creating very small and soft robots that could be swallowed and navigate the various passages in the human body. I mentioned biohybrid robots. So if we can create micro soft biohybrid robots, the human body is much less likely to reject those foreign bodies. There's a lot of microsurgical and intelligent drug delivery applications, I think. I think those used to be science fiction, but it's becoming almost possible to do this with human subjects. So I think that is a likely domain for the killer app for soft robotics.
So do you think there's challenges in the longer term, big challenges for soft robotics that you think facing this to become into reality, have this application from the lab to reality?
I think the big challenge, again, like any new field, is the hype cycle. So soft robotics has been around for a few years now. It's very exciting. There's been some very high profile publications in Nature Science and PNAS about soft robotics. And there's the feeling in the field, as usual, which is, well, now what? What can we do next? And I think every academic discipline and every technology goes through this cycle of intense interest and then a leveling off and a focus on the nuts and bolts challenges of the field. So the funding agencies also follow those hype cycles. So one of the challenges I think we're going to face is being able to communicate to our funding agencies and our industrial partners about why soft robotics continues to be important and is worthy of financial support.
So I would like to ask you about the brain. In your book that you mentioned that we don't have to, brain is not enough alone. So do you think that because there's current research about using microfluid as a controller and not relying anymore more law about using microcontroller, do you think this kind of research worthwhile to go in soft robotics? Go on. What are your thoughts?
Yeah, absolutely. And it's really interesting because we're going from microcontrollers towards microfluidics and other non-neural, signaling mechanisms for our soft robots, which is the opposite of how nature did it. We have a funded collaboration with Mike Levin, who's the director of the Allen Discovery Institute at Tufts University. And Professor Levin's group focuses on regenerative biology. And specifically on bioelectric signaling in organisms. So the fact that cells within organisms speak to one another using lots of different communication channels, including electricity. And they've used that to coordinate behavior, or organisms have used that to coordinate very complex and intelligent behavior long before neurons and synapses ever evolved. Neural systems are one of the last discoveries of Mother Nature. Yeah. And it's kind of interesting that in the history of AI and robotics, neural networks were sort of the first invention, and now we're moving away from neural networks, or at least thinking more broadly about other kinds of ways to imbue our machines with intelligence without having to rely on a massive neural network controller.
Do you think there's a limitation maybe for this technology in the long run, limitation for it?
I think my guess, and who knows where the technology will go, is that as usual, it will be all of the above. So organisms continue to, the cells within organisms continue to communicate with one another in non-neural ways, even in organisms that have nervous systems. There are pros and cons to communicating information through a nervous system, and there are pros and cons to communicating chemically and electrically, but non-neurally. And again, Mother Nature has found ways to combine those two mechanisms together, or those complementary mechanisms. You can imagine robots as well, where a neural network controller made out of electronics is useful for part of the robot's behavior, but there might be chemical or microfluidic other signaling systems within the same machine that support intelligent behavior under other circumstances.
So what is
it would be overly simplistic to think that one signaling mechanism is just going to be better than the other, and that'll be the only one we use in future soft robots.
So what are your thoughts about integrating emotions with soft robotics, like cuddler robots, soft robotics? Do you think this is something could be reliable to add emotions to robotic, or something is not important?
I'm sorry, did you say
emotions? Emotional soft robotics.
Emotion in soft robotics. Yeah, I'm not really an expert in affective computing and emotion. I do know, obviously, that humans attribute emotion to other humans and animals based on facial expression and that sort of thing. So you can imagine soft robotics would be useful there. It might be much easier for a robot to signal an emotional state through changes in its body. So it could be useful there, but that's not really my area of expertise.
Okay. So could you please tell us more about your ongoing project, incoming, interesting projects you are planning to work on?
Yeah, so we've got some interesting projects that are coming up. One of them is an integration between soft robotics and language. So you can imagine trying to tell a robot to do something, and in its current shape, it may not be able to perform that task. So how does a robot change shape when it hears natural language from a human handler? So this is something that kind of goes beyond what you see in nature. If you look at natural language processing in AI, it's usually non-embodied. It assumes that the natural language is parsed through a neural network. And even when we have embodied approaches to natural language processing, like in human-robot interaction, it's usually a rigid robot that isn't really able to change shape in response to natural language commands. And that's kind of an interesting direction that I think is an interesting direction that robotics hasn't tackled yet. A robot that assumes a different form when told to do something by a human handler.
Nice. So is there any project in soft robotics by other teams you think is interesting to you?
Oh yeah, absolutely. There's a lot of interesting things going on. I mentioned already biohybrid robotics, and there's a lot of interesting work there. The work on Vine robots, where you have a soft tube, and that tube is able to elongate through eversion or extruding additional material that's hidden inside the soft tube. I think that's fascinating. I mentioned already we collaborate with Rebecca Kramer-Botiglio at Yale. I think her robot skins materials are extremely interesting. In that case, in her group, she's demonstrated that you can take a robot skin and wrap it around a compliant but non-robotic passive material. And in effect, by wrapping it in a robot skin, you roboticize that object. You turn it into a robot. I think it's a fascinating technology in and of itself. But even more exciting, it's a great demonstration of this idea of how thinking about soft robots takes our thinking about embodied cognition in completely different ways, and it takes it into areas that even Mother Nature hasn't really explored before.
So now more futuristic questions about, do you think that soft robotics can have a singularity, reach singularity? Is this something do you think could happen?
I am not a member of the Singularity Church. The idea that any technology would grow exponentially, even AI, I think is overly simplistic. There are lots of arguments against that sort of exponential increase and improvement. So I don't think soft robots will get us to the singularity any more than traditional robotics and AI ever will.
So another question, how you see soft robotics in the future? That's just you can imagine how it would be, in what thoughts you have. Sometimes if you think, oh, maybe after 20 years this will happen, something you can imagine in your mind sometimes.
Yeah, I think, again, one of the things that I find fascinating about soft robotics is the material science side of it. I have a lot of colleagues working on very exotic materials. Rob Shepard at Cornell is doing amazing work with metal foams and other kinds of exotic materials. I think that's just going to continue and completely transform robotics. We're going to be developing materials that we don't understand very well, let alone know how to combine them together into useful autonomous machines. And I think, and I hope, obviously I'm biased, but I hope that will finally demonstrate the potential of evolutionary methods. Evolutionary search methods are particularly well suited in exploring very non-intuitive search spaces where we don't have a good idea of the constraints or even starting points for the search process. It's extremely difficult to take a blob of exotic material and apply inverse and forward kinematics to derive an optimal control policy. All of that infrastructure that's been developed in traditional robotics falls flat in the face of these exotic soft robots, and we kind of have to start again. I think that's one of the most interesting directions soft robotics can go in the future. And another direction that I think is very interesting is the idea of self-replicating machines, going all the way back to John von Neumann and the von Neumann machines that can build copies of themselves. If you have machines that are basically a continuum of material, you can imagine as long as they can get their hands on more of that material, it may be easier for them to make a copy of themselves than it is for a robot made up of steel and plastic and Raspberry Pis to create a copy of itself. So I think this future dream of self-replicating machines might become a reality with soft robotics in the not too distant future.
That's a great. So do you think there's kind of regulation that we have to come up with, or ethics to be considered in soft robotics so far?
Yes, absolutely. Obviously, robotics and AI is now grappling with the legal and the humanistic side and the ethical side of our technologies. We do some work in my lab on crowdsourcing as a way to create safe AI or safe robots.
Mm-hmm.
Look at the legal system. Technologies are proved to be safe if whatever that technology does, when it performs an action, humans looking back on what the robot did or what the technology did, if most humans feel the tool did the best thing it could do under the circumstances, then that was a safe machine. If anything went wrong, it was the human operator's fault.
Mm-hmm.
We're using crowdsourcing to do the same thing. So through websites, allow very large numbers of non-experts to collectively train robots. And we find that robots trained in that way versus training them by one grad student against an objective function that grad student came up with. Mm-hmm. Those crowd-trained robots tend to be judged by the crowd to be more safe than a traditionally designed robot. So we're working on applying this crowdsourcing idea to our soft robots as well.
Mm-hmm. So I have a question: how we can make sure that soft robotics could be beneficial to human in general in our research? Yeah.
The short answer is we cannot. In my belief, there is no way to proactively guarantee that a technology will not be abused.
Yeah.
What I feel we as scientists and engineers, our responsibility is to try and understand that technology as best we can and demonstrate all the different ways that it could be used and also abused. And it is then up to legislators and industry and the general public to decide whether and how to deploy these technologies in different domains.
Mm-hmm. Great. So do you think that soft robotics find its room in industry? And now, given to the industry we have, do you think that soft robotics can find a room now in industry?
Yeah, it obviously is already starting to. There are small companies like Other Lab in California that are creating soft and inflatable robotics. NASA's very interested in the technology, creating inflatable space stations or inflatable robots in space and non-terrestrial environments. I think there's a lot of practical applications there. And as we already discussed, the clinical domain. So there are a lot of industries that are looking at intelligent drug delivery. Some of those intelligent drug delivery methods are robots, and some of those robots are soft robots. So I think the clinical domain in particular is where we're going to see a lot of the initial commercialization of soft robotics.
Mm-hmm. So if you're a PhD student after graduation tell you he wants to start or she wants to start a startup, so what do you think the most important criteria to have a successful company in soft robotics from your perspective?
Well, I don't know because I haven't done that myself. But okay. Again, watching from the sidelines, if it's a soft robotics startup, I think, again, a startup in the clinical domain is the right place to start. Mm-hmm. A starting team would probably be made up of a computer scientist and at least one material scientist or materials engineer. I think if a team of people that are experts in materials and people that are experts in computation, if they can get together and come up with a unique idea and find an industrial partner that has an idea about how to apply that technology in an interesting domain, there's definitely a lot of room out there for some successful startups in soft robotics.
Mm-hmm. Great. So do you think that we have to come up with terminology to define the integration between machine learning and soft robotics? How do you see this integration is happening in nowadays between AI?
Yeah, that's a good question. Again, soft robots means different things to different people, and machine learning means different things to different people. But generally speaking, machine learning, at least these days, means deep learning. So some sort of neural network and finding enough data and getting Google to donate one or more data centers to train those networks. That's state-of-the-art machine learning these days. There is a movement within machine learning towards architecture search. So even the machine learning insiders are realizing that machine learning methods are greatly influenced by the cognitive architecture of the deep network, and that it's hard to design those by hand. So there's sort of this second phase now in machine learning research where they're relaxing some of their assumptions about the architecture of the neural networks. And some within the field are now moving into what I see as phase 3, which is realizing that at least in robotics, such as deep reinforcement learning, that those deep networks are operating inside a robot body. And if that robot body changes, it changes the nature of sensor motor data that's available for training the neural controller. And so there are questions, the machine learning researchers themselves are asking, how do we go about designing the robot itself to facilitate deep reinforcement learning? That's where machine learning research comes into contact with robotics in general and soft robotics in particular.
Wow, that's great. So do you think that soft robotics is gaining attention to the general public? It's really aware how this technology could be interesting in coming years. Do you think that?
I don't think so. The way that robotics usually comes into the public consciousness is through a viral video from iRobot Corporation or Boston Dynamics.
Yeah.
Just yesterday, OpenAI demonstrated a robot hand that could solve the Rubik's Cube, and there's already been several million views.
What's your suggestion about that? Because you mentioned that we didn't have enough robots, only the Roomba and coffee machines. So what do you comment about this news, this survey we had?
Yeah, well, I think, again, it's something that when you see the video, it's immediately obvious to the general public that there's been some advance here. It's something they've never seen before. It doesn't require a lot of technical explanation. And again, there's been a lot of viral videos around soft robotics as well. But I don't know if the public, recognizes this distinction between traditional robotics and soft robotics as much as those who work in the field do. I think that distinction is much more important and exciting to those who work in the field than the general public.
So do you think there's a solution or commitment we have to do in this regard?
I'm sorry, could you say that again?
A commitment for that. Do you think that we have to do something to push forward awareness about robotics for public?
Yeah, I think it's very difficult from the top down to plan to capture the public imagination. It's something that usually happens bottom up. Someone in the field introduces a completely new kind of soft robot, like Rebecca's robot skins or the Vine robot, and that video is released on the net and collects a lot of views. I think that's the way that we capture the public imagination.
Great.
I think I mentioned the clinical domain. If soft robotics become useful for actually helping with medical conditions that are difficult or impossible to tackle with human surgeons or traditional robot surgeons, that will be something that the general public can understand. If they can swallow a pill and understand intuitively that that pill is a robot that is operating inside their body, they will have a deeper appreciation for this particular kind of technology.
Great. So now more philosophical questions. Do you think ego is important for a researcher to be successful?
Ego, that's a good one. I don't think ego is necessary. What I think is necessary is unflagging optimism. So you've probably had the experience as a researcher, as we all have, of you have some great idea and you try 1, 2, 10 different ways of realizing that idea, and none of those experiments pan out. Successful researchers are able to still be optimistic even after the 10th failure and try an 11th or 100th or 1,000th attempt. Unfortunately, for a lot of people, unflagging optimism often is transmuted into optimism about themselves, which becomes egotism. So I think it's important to distinguish between optimism and egotism. It's important as a young scientist or as any scientist to be optimistic and believe that whatever challenge you're trying to address, either you or your student or your student's student may someday crack the problem. That's important.
That's good.
But being egotistical and thinking you're the only person to solve the problem, that's, in my experience, not that helpful in science or engineering.
That's a good point. So I would like to ask you whether you have designed a robot and built it in every day and ended up to be in your home. You have any robots in your home that you already designed?
I have. We've started to build some soft robots, and we make them out of soft, hollow voxels.
Yeah.
And I've got a couple of them sitting on my desk here, so they're not quite at home, and they're not the most functional robots, but they are very nice to grab and squeeze, so they're useful as a stress relief toy at the moment. Beyond that, I'm not sure.
So, as the PhD supervisor, what are the main qualities or you're looking for a student? Is it the skills or the trait? How you would look for a student to join?
So as I mentioned, one of the things I look for is relentless optimism. So when I interview an applying student, I ask them to tell me about a project they've worked on in the past. And what I'm looking to hear is, I tried this, that it didn't work. I tried that didn't work. I tried 3 more things, they didn't work. But on the 6th or the 7th or the 11th try, I finally got it to work. That's really what I'm looking for in a student. I'm obviously looking for some level of expertise. Most of the students that join my lab are pretty good coders. But beyond that, I assume that if they're relentlessly optimistic and curious, they're going to be able to teach themselves whatever else they need to know to operate in my lab. So that's really what I'm looking for, is kind of a personality type rather than a particular set of skills.
Great. So lastly, if there is advice was given to you as a researcher and was like a life-changing for you, and you would like to share with the audience?
Oh boy, that's a good question. Yeah, obviously throughout my own career, I've received lots of advice. I think the best one is a quote, and I'm blanking on the author of the quote, but it's perfection is the enemy of the good. So there is a tendency among academics or very bright people to be very detail-oriented and not to allow anything out of their hands until it's perfect. And I've known a lot of fellow students and colleagues along the way that fell by the wayside because they got caught up in some particular project and never managed to publish it or communicate it well to their peers. I think it's important to be relentlessly optimistic, to keep working at problems, and even if you only come up with a partial solution, to at least publish it and communicate it to your peers, knowing that they're going to have plenty of ideas about how you can improve that solution. I think that would be the advice that I would most pass along, which is to avoid perfectionism and instead focus on relentless optimism and generating interesting and novel partial solutions to really hard problems.
That's a great advice. So I would like to ask you if there's any final words you would like to forward to soft robotics community. Final words.
I think, and this has probably been mentioned by others on your podcast here, but it's an extremely exciting time to be in soft robotics. There are so many amazing new technologies that are meeting at the interface of soft robotics. 3D printing continues to leap ahead. Materials science. You mentioned microfluidics. Soft body simulation is becoming easier and easier. Integration with biological materials is now becoming easier and easier. I think if for those that are interested in robotics and AI, you never know, but I think most of the interesting problems in neural networks have been solved. There are many, many more open problems that can be solved by bringing together new emerging technologies in soft robotics, and that is likely to pave the way to new advances in robotics and AI.
That's great. Thanks so much for this interesting discussion, and both of IEEE RAS, I would like to thank you for your time. Thanks so much.
It was my pleasure, Marwan. Nice chatting with you today.
Thank you.